Today we're going to be talking about ratios and proportions. And the reason that ratios and proportions are so important is because we're going to soon be learning about what's called similar triangles, and actually similar polygons. And in similar polygons are defined by polygons that have the same shape, they have congruent corresponding angles, but they're different sizes. But to be exact, the sides of similar polygons are proportional. Very, very good. Okay? So in order for us to really delve into similar figures, we need to learn about ratios and proportions. And a ratio, I'm sure you remember from elementary, is a comparison basically of two values. It's basically like a fraction. Fraction is a ratio. You have, 3/8 of the pizza left. That means you have 3 remaining slices out of a total 8 that were once there. That is a ratio, okay? That's the ratio of what's left. The ratio of what was eaten then would be 5/8. So a ratio is a comparison of two values. Ratios can be written in 3 different ways. Does anyone remember the 3 ways that you can write a ratio in? As a fraction, one person says, yes. So I have A over B. You can also do A colon B, correct? And there's a word involved in there as a hint. 2, very good. You could go A to B. So those are the 3 ways that you can read and or write ratios. They all mean the same thing, okay? A to B, A to B, A to B. It's all the same, but you could write them 3 ways. Now, a slope. Slope is a very popular ratio that we've been working with already. And a slope, if you really think about it, is the ratio of the vertical change to the horizontal change. When you're talking about a slope, okay, you have a vertical change over the horizontal change. If you remember, slope we defined as being the rise over the run, where the rise is the vertical change, or the y2 minus y1 over x2 minus x1. Okay, that is a very popular ratio that we've already been working with. It's a rise over run. You're comparing the vertical change with the horizontal change, and therefore that is a ratio. Now, you see this little map here, and the reason I put the map here is to be a little archaic, I guess. I know that what I'm about to do, you guys don't have to do now in this technological world that we live in. You can go ahead and let's say you wanted to go visit the greatest university on earth, which was, no, that'd be UF in Gainesville. Okay, let's just say you wanted to go there for whatever reason. You're planning to go to Payne's Prairie. It doesn't have to be the university itself. But you know that on a map, okay, I can draw a straight line, and I can calculate the distance using ratios. All right. Every map on Earth has what's called a scale. And a scale tells you basically, okay, for this much distance on this drawing, it really equals this much distance in the real world, actual size. So just for giggles, let's just say that here 1 centimeter equaled, I don't know, okay, 50 miles. Okay? Just, that's random. If we went ahead and measured this, okay, from Gainesville to Miami, let's just say, for argument's sake, that that was 6 centimeters long. If I wanted to find the total distance, I set up what's called a proportion. We're going to talk about proportions in a second. A proportion is just basically two equal ratios. So if I know that my scale ratio is 1 centimeter to 50 miles, I want to find out how many miles am I going to be traveling for a distance of 6 centimeters on this map. Well, when you're setting up a proportion, I always like to think of like units to like units. So since I have centimeters on the top on the numerator, I'm going to put centimeters on the numerator here. And we were given 6 centimeters. I have miles in the denominator, so I'm going to set up miles in the denominator of my second fraction, which in this case would be x miles. So in this particular case, I would cross multiply, and x would equal 300 miles. Now again, I know that you can do this with MapQuest. I know you can plug it into the Garmin or the TomTom, any of these GPSs. I know that. I know that most of us can put it onto our smartphones. And in the smartphone, we just plug it in, tells us what we need. What if you ran out of battery? What if the GPS malfunctioned, which has happened to me? You got to use a map. In order for you to really understand what a map does, the power of a map, you need to know ratios. Let's say that you're in a rural road. That means there's not a lot of traffic around there. There's not a lot of businesses. And you know that in this one particular town, though, there's gas. Sometimes you have to calculate, do I have enough gas to get there? And the only reason you're going to be able to do that is by using these ratios and proportions. So although, for the most part, computers do this for you, it's really good to know how to do it on your own. So that's why you have a scale at the bottom of every map. It's not just because somebody wanted to write extra stuff there, but it's used for calculations. Okay, so now, that's a ratio. Now, linear functions, okay, remember, are based on a slope. If you remember, lines have equal slopes throughout the entire line. So when I give you a graph, I give you a line, okay? I can expand it if I want. Okay. Let's choose some random points. Let's choose this point here, this point here, and let's choose this point right here. Okay. Trying to prove here the slope is the same no matter what. And in proving this, I'm going to show you how to determine whether or not ratios are proportional. If I just go from this first point over here to this second point over here, am I not going down 1, 2, and I'm going over 1, 2, 3, 4? So I have negative 2 over 4, right? It's the rise over run. Now, let's say now I start with the same initial point over here, but this time I go down here. I'm going down 1, 2, 3, 4, 5, 6 over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right. This line, just, there you go. Sorry about that. Okay. 12. Well, I'd be going down negative 6 over 12 again. Now, these two bad boys are equal. We know that because they're very simple. It's negative 1/2 and negative 1/2. Let's say I had values that weren't so easy to determine. Well, I can go ahead and cross multiply. If I go 12 times negative 2, I got negative 24. 4 times negative 6 is negative 24. So basically what we're saying here is if the cross products of two ratios are equal, comma, then they are proportional. So it doesn't matter what point I start on this line, okay? Does not matter. What matters is that whenever you set up all the different possible slopes here, reduced forms or not reduced, you're always going to get to the same value because all of the ratios of a same line of a slope are proportional. They're equal. Okay? Does that make sense so far, gentlemen? May I continue? All right. Good stuff. So, proportions. Two equal ratios form a proportion. So I have two ratios here. A over B equals C over D. Very important for this lesson. There are names for these guys. You have the extreme over mean equals the mean over extreme. Okay? And the way you number these by terms, it's not left to right. It's up and down. So this would be term 1 is A, term 2 is B, term 3 is C, and term 4 is D. A and D are the extremes. B and C are the means. So when you have ratios and proportions, you have extremes and you have means. Extreme over mean equals mean over extreme. Extreme over mean equals mean over extreme. All right? And now we're going to learn some theorems. So let's first take the simplest theorem, the definition of a proportion. For theorem 59, in a proportion, the product of means equals the product of extremes. Remember that extreme over mean equals mean over extreme. So you have a proportion if and only if the product of the extremes equals the product of the means. Okay? So if the product of the extremes equals the product of the means, you have a proportion. And now we're just going to turn all of this upside down. It's very confusing, but again, it's very, very important. For theorem 60, excuse me, we're talking about the means extremes ratio theorem. I'm not going to go ahead and describe it in words because it's very convoluted. It basically means you can switch around the extremes and the means as long as you don't change the order of the products. Let me explain. Here I have extreme, mean, mean, and extreme. So in this case, PQ equals RS. This time I made the extremes P and Q. I made the means R and S. Well, check this one out. If I go RP over QS, I still get RS is equal to QP. Same thing. And then if I switch them out one more time, I go R over Q equals P over S, I'm still going to get RS equals PQ or QP. So the means extremes ratio theorem, you can make the extremes or the means anything you want. Okay? You can switch them around, but you have to switch everything around so that the original cross products stay constant throughout. Does that make sense, guys? Okay? I see someone saying no. Okay, talk to me. What doesn't make sense, my man? Thank you.
What you're just saying, actually was really like the extremes of the
The question was as far as changing around. Okay, do you see how you have PQ equals RS? I can change the extremes and the means around any which way that I want, as long as I get the product of RS and the product of PQ. I cannot do R over S Q over P. Cannot. That is not part of the means extremes ratio theorem because RP is not one of the givens. So you cannot do that. Now, what they're saying is, you know that PQ technically should be the extremes, and RS should technically be the means. So this first one right here goes right with the pure definition. The extremes were P and Q, extreme, extreme. The means were R and S. Well, you could have changed it. You could make the extremes R and S and make the means P and Q. You're still going to get RS equals QP. Or you could have changed R over Q equals P over S because you're still going to get, again, RS equals PQ. Does that help, sir? Thank you. Does that make sense, gentlemen? All right. Awesome. Let us continue. Now, using this means extremes theorem helps us out a lot for trying to figure out what's called the geometric mean or mean proportional. It does not mean that it's angry. It's just the mean as far as what the average is. Remember, there's a difference between arithmetic means and geometric means. If you remember going back in time a little bit, arithmetic means is like an average, and it would equal the sum over total number of values. Okay? It's like finding the average of your test grades, or finding the average of your homework grades, or finding the average of the fastest running backs in the NFL. Okay? You'd put up all, let's say, the top 15 running backs. You divide that number by 15, and that gives you the average speed for the top or fastest runners in the NFL. Okay? Now, geometric mean is a whole different ball of wax. Arithmetic mean, yeah, perfect. Sum equals, divided by number of values, that equals the arithmetic mean, or what's known as the average. The geometric mean is a little bit different, okay? In the geometric mean, what you always have to concentrate on is the fact that the means are always the same. They're equal. So extreme A over mean X must equal mean X over extreme R. That's how you find the geometric mean. Okay? Now, how would you do that if I say to you, find the arithmetic and geometric means between 3 and 27? Okay, someone just randomly blurted out a 9. I want an arithmetic mean and a geometric mean. So what would the arithmetic mean be? Some people are saying 15, some people are saying 12. Well, to find the arithmetic mean, wouldn't I find the total sum? 3 plus 27 is 30 over 2. So the arithmetic mean is 15. To find the geometric mean, we're trying to find the x. So to find the geometric mean, I have the extremes, which were given. 3 over x, which is the mean, equals x over 27, which is the other extreme. And you would cross multiply, absolutely, sir. So this would be x squared equals 81. You cancel out a power of 2 by taking the square root of both sides. They cancel. X equals plus or minus 9. And that would be the geometric mean. There would be two answers in this case, a positive and a negative. If we were talking about a shape or a figure, of course, the negative, you'd have to plug in to find out if it was positive or not. Does that make sense, gentlemen? Yes, sir.
They just gave you one mean to find out like the rest of the...
The question is, if they just give you one mean, could you find out the rest? No. No, but think about it. If I just said the mean is 8, okay, so I have a blank over an 8, and then an 8 over a completely different blank. How would you solve that? That'd be impossible. XY would be equal to 64. You don't know. There'd be several combinations there. So there's no way of knowing that. Now, if they gave you one extreme and the mean, then you're fine. Okay? You need at least, you can only have one unknown variable. All right. So now, let's do some examples. Go from easy to hard. Now, of course, in this one, this first one, it's just plain old, simple algebra. That's exactly right. 3 over x equals 7 to 14. Solve for x. 6? Yeah, it's absolutely right. Well, they did it fast because they looked at the logic. They said here, okay, first of all, my extremes are 3 and 14. My means are x and this 7. Okay? Isn't this basically 1/2? 7 14, isn't it 1/2? So isn't this down here double the numerator? Well, what's double 3? 6. Now, if you don't want to do it that way, you don't understand that way, no problems. Cross multiply. 7x equals 42. X would equal 6. So you could cross multiply it, or you could find equivalent fractions, whatever you need to do. That's pretty Mickey Mouse. Yes, sir. The question was, is this semester we're going to do more math than proofs? Yes. Yes. More math than proofs, yes. But there will still be proofs. All right, I don't want to lie to you. Okay. So let's continue. Okay. Find the fourth term of the proportion. Yeah. 2x equals 12. X equals 6. Done. Find the mean proportional, in other words, the geometric mean between 4 and 16. Okay, it would be 8. Let's see why. 4, which is the extreme over x, equals the mean x again, because when we're finding the mean proportional, we have to have equal means, equals 16. X squared equals 64. X equals plus or minus 8. So for those of you that answered 8 alone, unfortunately, that would be half wrong. Unless we were dealing with a figure. If we're dealing with a figure, you'd have to plug in that negative. If that gave you a positive value, because sometimes the side may be x plus 14. So if you had x was negative 8, well, negative 8 plus 14 is going to be 6. It would be valid. But if I had x plus 3, and I find out that x is negative 8, well, then you're out of luck. Because negative 8 plus 3 would be negative 5, and you can't have a side that's negative 5. So you'd have to plug it in when you get these two answers. If we're dealing with figures. If I just straight up tell you integrally, okay, just with numbers, then there's plus or minus. All right. Now, if 3x equals 4y, find the ratio of x to y. Think about what the definitions gave us. Yes, sir?
Like 4 to 3. Yeah, 4 to 3.
4 to 3. Very good. For those of you that couldn't see it, like me, I always look at what I remember about the definitions. 3x, isn't this the product of the extremes? And isn't this the product of the means? Don't I want x over y? So let's first plug in the extremes. X, and the 3 is going to be here because they're extremes, correct? And then the y, and the 4 because they're means, correct? 3 times x is 3x. 4 times y is 4y. So the ratio of x to y is 4 to 3. Talk to me, sir. Yeah. You sure, my man? Does that make sense to everybody? Yes? All right. Awesome. Great, great, great. Okay, now, is x over y equal to a over b equivalent to the proportion of x minus 2y over y equals a minus 2b over b? Yes. Why? How can we prove that? How can we prove that? How do we prove that ratios are proportional to begin with? It was theorem 59, guys. You cross multiply. So b times x would be xb equals a times y. That's ya. When we cross multiply over here, we get xb minus 2by equals ya minus 2by. The negative 2by and the negative 2by cancel, so I got xb equals ya. So, boom. We're good. Does that make sense, sir? Does that make sense to everybody? We're good? Awesome. All right. Thank you very much. Good lesson.